Okay, so we're going to carry on with our second part of oblique impacts involving smooth spheres. What that's going to look like is a couple of examples, a few questions for you to try, but this time making more use of vectors. So I think previously we sort of talked about how to solve the problem, and we did a few, but we didn't make that much use of vectors, that is to say ij vectors or two-dimensional vectors. So the examples we look at today are going to make more use of that, and the questions as well. So then just to get started, this is almost a geometry problem, more so than anything that involves thinking about momentum or anything like that. It's a kind of geometry problem, but it is one in which you need to be very careful to follow your understanding of how the rules work in terms of how velocities change when the spheres collide. So the situation I'm giving you is you've got these two red balls. They're vertically aligned, everything's sort of at 90 degrees on a sort of square grid. These two red balls are the same size, and then a blue ball, also the same size, comes along and goes cleanly into the center of them. So effectively the blue ball is going to hit both red balls at exactly the same time. Okay. No information about masses or speeds. It's actually not relevant. What is relevant is they're all the same size. The question then is, at what angle is either of these red balls going to shoot off at? Right. If we take the horizontal as 0, is this red ball going to be going at what particular angle to the horizontal? That's my question. Right? Is it 15, 30, 60, 90? What is the angle it goes off at? Have a think about it. There's probably a couple of numbers that immediately jump to your head where you think it's obviously that, but do make sure you take the time to think it through and double check that the logic you've used to get to that number makes sense. So it's a bit of intuition, but you also want to make sure you use the definitions we've talked about earlier, common tangents, line of centers, and that sort of thing. Okay, so give that a go, and then we'll go through it. You can pause now. Okay, so in this case, this is mainly about considering the diagram when all three balls are touching at the same time. So when that blue ball hits the two red ones, what you're going to end up with is 3 contact points simultaneously. Okay, and only the blue ball has a velocity, and that blue ball is going to hit the two reds at the same time and give an impulse to both of them. Okay, the reason that we even really might want to consider the fact that there's 2 red balls rather than 1 is all about the geometry of where the balls are positioned. But once we've thought about that geometry, we only have to really concentrate on one of the red balls and the angle it makes. The other red ball will make the same angle, just in the opposite direction, downwards. So when these 3 balls are touching each other, we kind of have a symmetry, right, with a sort of 3 cycle. So those 3 balls are almost interchangeable, right? I could rotate the image 120 degrees, I'd have exactly the same image again. So what that tells us is that, therefore, since each ball, from its perspective, is no more unique than the other, what we have here is an equilateral triangle, right, between these 3 contact points. And furthermore, not only do we have an equilateral triangle there, we therefore also, by thinking about radii and the fact that they're always perpendicular to the contact point, we're going to have an equilateral triangle through the lines of centers as well. And that's probably the more important equilateral triangle to think about. Okay, so that's as a consequence of the fact that there's 3 balls touching all at once. Right, so now that we've established that that's an equilateral triangle by virtue of symmetry, let's just draw the top red ball and the blue ball there, mark on their centers, and I'm going to then mark on this line of the equilateral triangle here, and then I want to think about, right, what does that line actually represent? This effectively is the impulse, right? Oops, this is the impulse, which, you know, red is going to experience an impulse, blue will also experience one in the other direction, but red is going to experience an impulse, a change in momentum in that direction, and because it currently is at rest, that means its velocity is also going to be entirely in that direction. So what we're saying is that the red ball will move in direction of impulse. Okay. Remember, that's not always the case. It just happens to be the case here because red is originally at rest. Okay. The red ball moves in the direction of that impulse. So then finally, we just need to think, what is the angle? Well, because we said it was an equilateral triangle, if we mark on that other line there, that's 60 degrees. The horizontal passes perfectly through. So therefore, our final answer is this angle here, which is half of 60, so it's 30 degrees. Okay, the top ball, red ball, is going to go off at 30 degrees upwards, and the lower red ball is going to go at 30 degrees downwards. And if you thought the answer was 60, which you might have done, then make sure you understand why that doesn't make sense and 30 does. And perhaps you might think the answer is 60. That would make sense if the blue ball hit the red direction, hit the red ball, sorry, going in that 60-degree direction of the impulse, right? But in this case, yeah, well, I'll let you decide what you think the reason is, but the answer is in fact 30 degrees. So let's look at our first example involving vectors. So we've got smooth sphere A, mass 5 kilograms, smooth horizontal surface, and now its velocity is a vector 2i plus 3j. Another smooth sphere B, mass 3 kgs, same radius, same size, as A is moving on the same surface with velocity 4i minus 2j. The spheres collide with their line of centers parallel to j. That's probably the first bit of information we need to actually draw the diagram. So the line of centers is parallel to j. In other words, it's vertical. That's our line of centers. Let's then draw the spheres on with their centers both on that line, such that they've just collided. The coefficient of restitution is 3/5. And now let's draw on the velocities. So the first one, let's say top is A, bottom is B. Does that make sense actually? 2i, 3j, and then 4i might, I think by nature of the fact that they've actually collided, that might be slightly different. If we look at their y components, one of them is positive, one of them is negative. So for them to actually hit each other vertically, it must be that the 2i plus 3j is on the bottom. Okay, so this must be A and this must be B. So it's 2 plus 3j, let's say there. I'm just going to call it 2, 3. And it's 5 kgs. And our other ball is going 4 minus 2. Something like that. And that's 4 minus 2. Okay, so that's how they hit each other. At the moment of collision, they are vertically aligned in that sense, and they've got those two velocities. Find the velocities of both spheres after the impact. So in this case, probably easiest to just draw the after scenario and then just immediately add what we know. So we've got our two balls there. And what do we know? Well, we know that the velocities that are going in that direction, the common tangent, are not going to change. So therefore, the velocity of this first one is going to be something for something, right? For something. We don't know, because the horizontal direction is the one we know stays the same, right? So it'll be for something, and then likewise here it will be to something is the velocity of that one. So now let's obviously replace those somethings with some variables. Pick what we like. Since these are scalars, let's just give them scalar type variable names. Let's avoid u and v. Let's call them s and t. And now we can just use our usual conservation of momentum and coefficient of restitution information. So coefficient of restitution tells us 3/5 is equal to let's say so final s minus t, so I did the top and the bottom divided by it, and then let's do the bottom minus the top. That is a minus b. So a's initial horizontal speed was 3 and b's sorry, I'm talking vertical speed, aren't I? So a's initial vertical speed, sorry, was 3. B's initial vertical speed was minus 2. So we end up with this. Okay, let me just double check that makes sense. So I've gone, in this case, with final velocities, I'm only looking at vertical. A first, or let's say, sorry, B first, S minus t, divided by, and then we'll do A first, and it's 3 minus 2 equals 5. Okay, yeah, that should make sense. So then we get S minus t equals 3. And that's our first equation in the vertical direction. Then conservation of momentum. So vertically, initially we had that minus 2 times 3 plus that 3 times 5. So that's 15 minus 6. We can do it in one go. So by conservation of momentum, we have initially 9, and then finally 3s plus 5t. Okay, so then we can do some solving. Let's change that s minus t equals 3 to 5s minus 5t equals 15. Let's add those two purple ones, and we get 8s equals 24, which tells us s equals 3. And if s equals 3, then by this one I've underlined in green, t must be equal to 0. Okay, so we've done it. So our unknowns, our s and our t, are actually 3 and 0. So now we can actually draw on the velocities if we so chose. It goes like this, at 4, 3. And then this one actually just goes horizontally only. So A is conveniently knocked in such a way that it then ends up just going perfectly horizontal. Whereas B sort of ends up going back on itself. Okay, good to keep in mind that you don't actually know for sure that when they both hit, like with normal collisions, that they both then separate in opposite directions. It could even be the case that A continued going upwards, but just at a lower angle. There's no reason to assume that it necessarily goes down. So you've got to be a bit careful of that. But that's it. We've done the velocities. Should be 4, 3 for B and 2i, or just 2 in the x direction for A. Okay, and then final example. This one's interesting because it doesn't tell you how the two objects hit each other. So at what angle. Effectively, we don't know what the line of centers is or anything like that. So we can see how we can work now with knowing everything about the velocities, or knowing most things about the velocities. We can work back from that and figure out what angle they hit at. So in this case, we've got A and B equal radii, mass 2m, mass 3m. they move on a smooth horizontal plane, bird's eye view, and they collide. Before collision, A is going up 5j, B is going up 3 minus 1. Right, so A is going something like this, and B is going something like this, specifically 0, 5, and 3 minus 1. But I hesitate to draw the circles yet because I don't know in what configuration they hit each other. Immediately after the collision, A has a speed of 3 and 2, so something like this. Okay, and then B is unknown. Okay, and that was our initial, and that was our final. Okay, so what I'm saying is we don't know how they hit each other. We could make up anything that uses these two vectors, right? Pretty much. I could say maybe when they hit each other, it looked like this, and you know, A. Let's say this was A going up here, and then B was going like that, or maybe they hit each other. Maybe they hit each other even perfectly vertically like that, and then we had A going upwards and B going down like this. So that's what I'm saying, is we don't know actually in what angle, what configuration they hit each other. So this is where you really start to notice that we're really not modeling these as particles anymore. If these were particles, none of this would be of a concern. But in this case, because they're sort of physical spheres, it makes a difference. It's going to affect what ends up happening. So because we don't actually know, what we're going to have to do is, well, I suggest let's actually just work on B, because I'd be interested to find that what that looks like, what's the actual configuration, and then we can do A afterwards. So to find this this line of centers in B, right, what we have to remember is that the impulse is always parallel to the line of centers. Okay, so that is to say, you've got your two objects. If they hit each other, then the impulse is going to be along that line, right, in both directions, and that applies to both of those two objects. So what we can do is, let's work out the impulse of A, because A, we know exactly what happened initially and finally. We have its initial final velocity, therefore we can find its change in momentum, and change in momentum is the same as impulse. So the change in momentum or impulse for A is going to be its mass of 2m times final velocity minus initial velocity. Okay, and what that gives us is 2m times 3 minus 3. Now, the multiplying scalar, the 2m, doesn't really particularly matter. In fact, neither does the fact that 3 is a factor of all of these. We're just going to say IA is direction, and let's just pick a simple vector. In this case, I'm going to pick 1 minus 1, which is clearly a multiple of this one, right? It's basically dividing it by 6m, and we get this. That's the direction. So now we can actually accurately draw what's happened. I'm just going to rub all this out, other than to note that the impulse A is 1 minus 1, right? Not equal to, it's in that direction, right? IA is in that direction. Maybe because it might be relevant for an earlier section, let's actually note down the full one there. Okay, so we've got the impulse, it's 1 minus 1, and of course if you picture what 1 minus 1 looks like, it's effectively going 45 degrees down, or it's like the y equals minus x line, isn't it? So that tells us that the line of centers looks like this. Right, that's in the direction 1 minus 1, or minus 1 1, same thing, right? Now we can draw on the balls, or the spheres, just because it helps a little bit with the visualization of what's going on. So this is how they actually hit each other, right? And then we know which one's which. This must be A here, going upwards, and this must be B here, going along like this, 3 minus 1, at least initially. Okay. So then that might help us with visualizing what's going on with the other questions. For part B, it does say a unit vector parallel to the line of centers. So actually we can just very quickly answer part B now, and we can say I hat is going to be equal to, well, 1 minus 1 is a unit vector. We're going to have to divide it by the magnitude. The magnitude of that vector is root 2. So it's going to be 1 over root 2 minus 1 over root 2, or root 2 over 2, whichever you prefer. Okay, so that's the answer to that one there. You could alternatively have, of course, minus 1 over root 2 and plus 1 over root 2. Again, it doesn't matter. You're just multiplying it by minus 1. It's still the same. Oh, it's not the same direction, but it's still parallel to the line of centers. Oh dear, I've just realised I've drawn this wrong, obviously, haven't I? What I've done there wasn't the line of centers at all. Oops. Sorry, the impulse is correct there, but when I drew it on, I drew it as the common tangent. Sorry. So yeah, that makes more sense. Hopefully you spotted it before I said something. So yeah, that makes more sense. Impulse that way, impulse that way. So let's look again at the A and the B direction. Can we tell which one's which? Yes, we can. It only makes sense for this one to be A, going straight up, and it makes sense for this one to be B, going along like that. Okay, that makes more sense. Cool. All right, so what is the speed of B immediately after the collision? Well, this we can answer quite nicely now, because we have the impulse, right? And we know the impulse on B is going to be the opposite of the impulse on A. So the impulse on B, let's write it here, the impulse on B is going to be equal to 2m, and equal and opposite, so instead of 3 minus 3, it will be minus 3, 3. So our change in momentum of B is this. Let's then find the change of momentum by using an unknown vector v as our final velocity for B. So we'll have the final velocity for B minus its initial velocity multiplied by its mass, which is 3m, and all of that is the change in momentum, which is therefore equal to 2m minus 3, 3. The m's cancel. Let's multiply out. We get 3v, let's say plus, let's not say plus actually, that overcomplicates it, minus 9 minus 3, and that's equal to minus 6, 6. And then with a bit more simplification, you should be able to see the final answer is in fact just 1, 1, right? So 3v becomes 3, 3. Take away 9 minus 3 from that, and you get minus 6, 6. So that's it. V equals 1, 1. It looks something like that. Okay, and then the final answer here, speed of B, is just the magnitude of 1, 1. So we get root 2. Okay, done. So a bit more to consider in terms of vectors for those last few examples. Don't make the mistake I did, which is confusing line of circles with the common tangent. Remember that the impulse always acts along the line of centers. And I think even just a line of circles a moment ago. It acts along the line of centers. and the two impulses will always be the same magnitude but just in the opposite direction. So that's quite a useful way to find a missing velocity if you have the other three in terms of vectors, because then you can find the change in momentum of one, flip it by making it negative, and then use that to find the missing velocity for the other sphere. Okay, so I'll give you a chance to do some questions now. So there's 2 questions here, followed by a third on the next slide. That one's a few more marks, a bit more challenging. So do make sure you give yourself time to get to that one. You can pause the video now, give these 2 a go. Okay, and finally have a go at this one. 6 marker, an interesting one. Can you solve it? Give it a go. Pause now.